So before we move forward with that one, we need to know the series capacitors and in parallel the parallel capacitors. So for example, I'm drawing this circuit, and you let me know what's overall capacitance here, what's C total, and why. Do you know why is that? So we are going to derive it, and you'll know. What about this? What's the overall capacitance? So it looks pretty similar to the parallel and series resistors, but just reversely. Why is that? I mean, theory. It's not from nowhere. It's a numerical number here. You have to derive it from maths. So we can treat every single one here as a single resistor, as an impedance, right? So what's the impedance of this guy? What's the impedance of this guy? Okay, that's the impedance, and we just can use the parallel resistor equation to find out the overall capacitance. Can I do that? So the overall capacitance impedance, right? 1 over j omega c total, the overall impedance of the two terminals equals to what? Just treat them as single resistors. So it's going to be 1 over j omega c1 times 1 over j omega c2 over 1 over j omega c1 plus 1 over j omega c2. Is that right? You still remember this? Parallel. Yeah, because there are two impedance in parallel, or two resistance in parallel. The impedance is being used for the AC term, right? And now let's find out what we can do here. It's going to be 1 over, let me and then what? Flip it, right? It's going to be 1 over j omega c1 times j omega c2 times c1 plus c2 j omega c1 c2. So what can be cancelled? Right? What's the final result? Okay, did I make any mistake anywhere? Nope. So compare these two equations. Let me know what is C total. It simply just replaced C total here with C1 plus C2. That's why this makes sense. What about this one? this one. So we can transform this to what? C1, C2, C1 plus C2, right? So let's find out if this one is a overall capacitance over the two terminals. So 1 over j omega c total equals to what? Equals to what? For the two impedance in series. Just add them together, right? In series. And then j omega c1 c2 c1 plus c2. What's next? What's next? Compare. Still not reaching there yet. What's next? I don't need to calculate anything. I just need to find out at this location what is the C total in here. Yeah, you just want to try to isolate. Just make a 1 on the top and j omega times something. You just want to transform this format into that format so you can compare with the C total's location, and you can get what is C total, right? Or just like what you said, you can directly calculate, which is fine too. But let's do this way. So I just put 1 on the top, and what's going to be on the at the bottom will be j omega c1 c2 c1 plus c2. Right? Since you divided this guy, you flip it. Right? So this will be on the top. Then compare. C total is this. So it looks exactly like the parallel resistors, but actually they are in series, right? So keep in mind. Still need it? All right, let's go to the next one. Important. Will be on the exam and lab and also homework assignments you are going to work with. So here's the circuit. (12 volts), amplitude 60 hertz, frequency 30 ohms. That's V in, this node. Here's V out. It's 100 microfarad. Is 100 microfarad large or small? Micro. Micro. But farad is a huge unit, same as amp. How many amps can kill a person? Can kill a cow? Can kill a cow? 200, 300 milliamps. So ampere is a huge unit. Farad is a huge unit as well. So usually, if you grab a breadboard or something, so you have all the wires and metals inside the board. If you measure the parasitic capacitance of the board or something, it's something around like 20 picofarad. 20 picofarad in the wire, in the cable, or in anywhere. But however, 100 microfarad in compare with the pico, it's like 100 million times larger than that. It's a huge cap. Huge. So the question here is, what is V out over V in? I just make it simple. VO over VI, which is attenuation. And what's the time delay? time delay, I put a T here, which means the unit should be second, not angle. You have to convert angle into second. Now let's work on this pretty standard problem you are going to see in homework assignments and quizzes exams anywhere. So what's the impedance of this guy? 1 over j omega c. Depends on the frequency, right? So this omega is 2 pi f. So that's why the impedance is not fixed. Depends on the signal's frequency. You are going to have a different impedance. So will this guy show you a low impedance with higher frequency or low frequency? I mean high impedance with low frequency or high frequency? Low frequency, this guy seems like a higher impedance because lower here, higher overall, right? Is that making sense, you think, intuitively? Not according to the number, but think about the frequency, saying, of the signal. If you inject an AC signal to a capacitor, do you think when you have a higher frequency, it's going to be easier to pass, or lower frequency is easier to pass? Higher frequency is easier to pass. So you can think about it in that way. So when the frequency is getting lower and lower, finally go to 0. DC is going to be blocked by the capacitor, cannot penetrate at all, right? That's why when it's getting higher and higher frequency, it's easier to pass the capacitor. So with the high frequency component for a signal, the capacitor is working as a short circuit. Little tiny resistance. It's going to short the circuit wire. Okay. Now let's get this one first. Is that a voltage divider? What is a voltage divider? You still remember that, right? What's the voltage here? Yeah, but what's the voltage? Voltage divider, let me know in 1 second. If you cannot. Yes. Why? You got current, right? So what's the voltage here? I times R2. What's the voltage overall? What's the time overall here? V in. You got current flow through these two resistors. Cancelled. VO over VI is R2 over R1 plus R2, voltage divider. What's the voltage here? It's hard to tell. Is that hard to tell? If you say it's easy to tell, then you got a mistake. Why is that? You're telling like 10K, 10K, so the voltage 10 volts will be divided by 2 halves. Is that right? Why is not right? Yeah. So it's not a voltage divider. Is this a voltage divider? It is, but you have to count 5K into that. You cannot just like look at this. You're saying, hey, voltage divider, 10 volts, 5 volts. It's not. The reason is these two guys, this one and this one, is not sharing the same current. Here, they share the same current. You can cancel the current, so it's a voltage divider. Here, they are not. So the current flowing to here, to here, to here. Not the same current. You cannot cancel that. So here's not 5 volts. It's lower or higher than 5 volts. Is that lower or higher? Lower. Why? So you put a 5K in parallel with a 10K, will reduce the overall resistance over here. So make it lower than what? Even 5K. So not mention 10K, it's even lower than 5K, probably like 3K or something, right? I think it's 3.3K. $53, 3.3K. So it's lower than 5K, so that's why this one will have a lower voltage than 5 volts. And now let me know, is this a voltage divider? Yes. Great. Now, what's the voltage? What's VO over VI? Let me know. Let's don't draw this absolute symbol first for now. What is VO over VI? Just use the impedance of the capacitor divided by the overall impedance. Over what? Is that right? And then what? Times J omega C on the top and at the bottom. Okay? And now let's find out the amplitude. Both of these two terms at the bottom and the top, they are phasors. One plus 0J. At the bottom is 1 plus omega RCJ. So what are the amplitudes? 1 square plus 0 square square root. 1 square plus omega RC square square root. Okay? Next, 1 on the top and 1 plus 2 pi f, which is omega, RC square, square root. And let me know what is this. 2 pi, 2 times. Let me write it down here. 2 pi f RC equals to 6.28, which is 2 times 3.14, times the hertz, 60 hertz, times R, which is 30 ohms, times 100 microfarad. And what is that? 3,000. So this will cancel this one and give you a milli. So 3 milli. 3 milli is 180 milli. (180) times 6.28. Wait, is that right? (180) times 6.28. Okay. And square, right? So the square is right. Looks weird. Yeah, milli, and this one will cancel 3 digits, and then give you a. Yeah. Let's say 1. Oh yeah, and then plus 1. Oh, square of milli. I'm gonna cancel 6 zeros, so it's gonna be 1.3. 1.3, so it's gonna be 1 over 1 plus 1.3. And 2.3, right? Square root of 2.3. 1.5. And 1 over 1.5 is 0.67. So that's this, and that's this. Okay, so the VO will be 0.167 of VI. So 67% of VI. That's the amplitude. What about the phase? Phase. We want to probably look at this guy. So that's VO, that's VI. Right? You're saying here's VO over VI. I transformed this to this. Is that still over VO over VI? It's keeping the same ratio of the amplitude and also keeping the same phase difference between these two signals. They probably are not exactly VO and VI, but there's no change for the phase difference. So for example, right now here's VO. You can find the phase of it, right? And you can find the phase of this guy as well. So you're comparing the two phase, VO, VI. You are going to make a subtraction between these two phase, these two signals. And now, for example, this one phase is here, one phase is here, right? After you transform it, it's going to be like this. So the phase difference is not changing at all, which is fine. So now let's just use this one, this tool, since it's easier. Let's see. The angle VO minus the angle VI equals to the inverse tangent 0 over 1, which is 0, minus inverse tangent of omega RC over 1. And that's it. That's a time delay of the VO compared to the VI, which is 0 degree minus, I have to calculate it. It's here we know omega RC is this one, which is this. Is this a 0 degree? 0? Oh, why 0 to 1? Because here 0, 1. Imaginary is 0 and real is 1. You still remember what is this value? 1.13. Okay, and now it's going to be 0 degree minus tangent, inverse tangent of 1.13. And what is that? 1.13. Yeah, negative. Do you know where I can find that? Just use the online calculator, or if you have a calculator can do that job, just do it. So 0 minus 58.5 degree will be minus 48.5 degree. So that's time delay in terms of angle. So what about the phase shift in terms of time? I'm asking you TD. T means time. So the unit should be second. So that's a sound wave, right? So ready to get an angle. Yep. So here's the angle. So what you can convert, how you can convert this one into angle, into time is use angle divided by what? So this is in degree, right? So we're going to use 360. So which is the share of this angle in the entire period. And what's the time? So you can convert into time. What is period? 160 hertz. It's a 60 hertz. So the period will be 1/60. So it's going to be 48.5 degree over 360 degree times 1/60. What's the unit? Delay? Yeah, seconds. So let's find out. Uh, 48.5 divided by 360 equals to this, and divided by 60 again. So that's 2.2 milliseconds, right? 2.2 milliseconds. 2.2 milliseconds. And when you are plotting the curve qualitatively in your homework or in the exam, so you draw the original signal first. Draw the original signal first. And then you're saying, hey, this is 0.67. So that's V in, just label VI. And the time delay is 2.2 milliseconds. And you don't know where to start with, which is fine. Just look at the angle. So the angle is about, so this is 90 degree, right? So this is about 45 degree. So 48 is a little bit more than 45. So you can tell this will be 2.2 milliseconds. And you start plotting your output here, but it's going to be, will only be able to reach 0.67 with the full range. 0.67 is here. So that's V out. Okay. Qualitatively, by doing that and verify with LT-SPICE. Let's see if it works in LT-SPICE. Yes, lagging. So when you're doing the homework, if I didn't say code it up, you just directly use the symbols. F2 will bring up the library and find out the voltage, put it here, and resistor, rotate, and cap. So after this class, what you can put on your resume? Additionally, AC analysis, LT-SPICE, AC analysis, IC layout, analog circuit design, analog AC design, whatever you want to put in there, just something related to this. Right? Sine wave, 12 volts. So amplitude, DC offside, we just don't put anything there, it's fine. Just say 12 volts. Frequency is 60 hertz. And time delay, no time delay. Let's put 0 here, just in case. And resistor is 30 ohms. Here is 100 microfarad. And label that V in, V out. And do a transient analysis, dot tran, because it's 60 hertz, so one period will be 0.01 or 10 milliseconds. So let's run 50 milliseconds. We have like something like 5 periods in there. Run. M. Oh, I got a space. Yeah. The space. V in, V out. Now let's test it. How do you want to test the amplitude? Yeah, 2 cursors. Double click V in. So got 2. Probe the top here. You know it's 24 volts, right? Since you assign that. you design that 24 volts. See, two cursors, and you look at here, 23.95 something volts. You cannot make it 100% perfect here, so it's 24 volts. You know that, and then double click this guy, and this one to here to the peak of VL to the bottom of the VL, and now let's look at the cursor, 15.8. Now let's use the calculator, see if it's 0.67 attenuation. So 15.88 over 24 volts, 0.66. Close. Verified. Okay, and make a snapshot of this one, of your circuit. So how can I make it? Just make it smaller. I will do that probably. I'll just do this. Just record both of the two cursors, the little monitor, the previous one, and also this one, so you can compare. And also the circuit. You can actually resize the window to make it probably like this, Okay. Make a snapshot and copy and paste to your homework paper. Do not landscape, which means you don't want to just use one page, just show one single figure. You want to make this figure not that large. Let me show you. I'll just do this, your homework, and copy, and go to desktop. So for example, this is your homework. So like 1.1, for example, that's a problem. I have all these things, and you leave some space for the calculation, right? Calculation for the space for the calculation, and also do simulation, and then paste the figure in here. Yeah, just like this size, which is the right size. And you can print the paper out later on, and so you can hand write your calculation in this blank area space, or anything you want to put in there, which is fine, but definitely do not landscape. Just keep the figure in the right size. Okay, keep the layout looks nice. So it's verified. There will be more examples. Six. Oh yeah. All right. Thank you. Time delay 1 here. Hey, if you know how can you bring up two cursors, follow two different signals, let me know. I sometimes I can accidentally do that. I did that a few years ago. I forgot. So see that control.
You just double click on one of them and then click on the other.
Okay. Yeah, let's see. Boom. All right. So this guy is following V out. This one is following V in. Great. So now I'm gonna point my cursor tool to the peak of V out, and I want to point this one to the peak of V in. See how I did that? Yeah. So the cursors. Okay, let me do that. Here. 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 So the horizontal difference, cursor 2 minus cursor 1, so this 2.2 milliseconds, which is what we got. All right, I think we don't have enough time to run another example today. So labs tomorrow. We'll see you tomorrow probably. AC circuits. Huh? Yeah, same place. I have to use a card to bring all these oscilloscopes and function generator over. I will do that.